Hey y'all. So in this set of series of videos, we're going to be looking at analysis of your testing, both your simulation and your wind tunnel testing, and figuring out how to compare our simulated data to full-size flight to see if our wind tunnel testing shows that, hey, we can move forward with this wing design. I share my screen. And we'll start with our simulation actually. Oh, there we go. Not floating mean controls. All right. So this is an example of a very thick or a thick cambered airfoil, 10%, 10.5% thickness, 10% camber. And we can see it makes a lot of lift. It makes plenty of lift even at a relatively low angle of attack. And then it doesn't have the best, according to the simulation, it doesn't have the best lift to drag ratio in cruise. It doesn't matter. The analysis you'll do would be the same. So in this video, we're going to consider takeoff. In the next video, we're going to consider cruise. So remember, we want to be able to take off at 40 miles per hour and 5,000 feet. Oops. Oh, I don't know why I tried to move that paper with my mouse. All right. So remember the formula for lift. Lift is equal to 1/2 the density of the air times the velocity squared times the area times the lift coefficient. Now we're dealing with matched velocities, but we're dealing with different air densities, different wing sizes, areas, so and different amounts of lift. But the coefficient will allow us to compare the two. So if we solve this for CL, CL would equal, we multiply both sides by 2, to L over rho V squared A. So for takeoff, we would have, let's see, we need to make 1,000 pounds of lift. So 2 times 1,000 pounds. Now, the density of air we had in our spreadsheet from before, the simulation example, at 5,000 feet, the density is 0.00205 slugs per cubic foot. Then for velocity, and this is CL, we need to convert miles per hour to feet per second because in imperial units, that's the standard speed. It's kind of like the equivalent of meters per second is in the metric system. So this is 40 miles per hour, 40 miles in 1 hour. We need to get rid of miles, so put it down here. And 1 mile is 5,280 feet. That'll cancel. We need to get rid of hours, so we put it up here. 1 hour is 3,600 seconds. And we can see we're left with feet divided by seconds for a unit. So that's 40 times 5,280 divided by 3,600. All right, that's 58.7 feet per second. 58.6 repeating feet per second, not feet squared. Then we will need feet squared in a second. Feet per second. All right, anyway, so that's 58.6 repeating feet per second, all squared. And the wing area was, since this was a 6 by 32, the wing area was 192 square feet. All right, so we have 2,000, because 2 times 1,000, divided by 0.00205, divided by the 58.6 repeating squared, divided by 192. So that's saying to take off, that requires a lift coefficient of 1.47. Just to check, yeah, we definitely achieved that in this simulation. So that's saying to take off, we need, yeah, a lift coefficient of 1.47. All right, I'm going to star that. We'll come back to that later. Let's look at our simulation, or sorry, we'll go from our simulation, though, before we move on. Notice how there's this region here between where it stalls in the negative angle and it stalls at a positive angle, and the lift starts to decrease, where this is basically linear. That the slope of that line, or here, if we look at the coefficient, is called the lift slope. It's the slope per angle of attack. So if we look at our experimental data, we're going to do some modifications here. We want to find the slope of this linear region. So what I'm going to do, click on the graph with the data filled in, the lift coefficient versus angle of attack, and do Control C. Or I can also click down here and say copy chart and then paste it. And I want to trim out these non-linear regions. So starting here at like 20 degrees, this is where, so like here between like plus 20 and negative 10 or something like that is where it looks fairly linear to me. Wait, that's 80 miles per hour. We're going to need that later anyway, but I'll delete that for now. Sorry about that. Well, again, between like, say, plus 20 and in this case, negative 5. Or even, yeah, positive 15 and negative 5. That's where this trend looks pretty linear. So I want to make a copy of this graph. You might have to make your Z cell really big. That way when you copy chart and paste it. All right. So now I do click on that, edit chart, and I want to change the range of data here. So I don't want to consider anything before negative 5 degrees. If we look over here, negative 5 degrees, that's what, row 12. So over here on the data range, I'm going to delete where that says D6, I'm going to change that to D12. And where this says G6, I'm going to change that to G12 to make the lower bound of, and then press enter. So now the lower bound of that is at negative 5. I've cut off all the other stuff. And I want to go to like positive 15 right here. It already does start to curve off here at 20. So 15 degrees angle of attack. What row is that? Row 16 in this case. So I want to make the upper bound for all of these 16. So change that to D16 and G16, press enter. And now I've cut off the nonlinear regions. Then I can go to Customize, Series, Trend Line. It's already defaults to linear. And under Label, Use Equation. And that'll give me the equation for this. All right, I'm going to close that menu. We'll keep this. And let's continue or return to our paper, because we're going to need to look at that. So that'll give us the equation it gave us the equation y is equal to 0.0907 times x plus 0.395. But our y-axis here is the lift coefficient CL. And our x-axis is the angle of attack. So that's equal to 0.0907 times alpha plus 0.395. Interesting thing. So this intercept there, this is telling us that even at 0 degrees angle of attack, with the plane flying completely level, or if the wing completely level, because of the camber, there's already a lift coefficient of 0.395. That's what that intercept is. But a lot more useful for engineering purposes, we graph CL versus alpha. We want to find the angle of attack that gives us no lift, the no lift angle of attack. In other words, we want to solve for the angle of attack when our lift coefficient is 0. So we want to kind of put this into a point slope form, where our point is this alpha naught, the 0 lift angle of attack, and 0. So if we solve that, let's see, we would get CL, or set CL equal to 0. 0 is equal to 0.0907 times alpha naught plus 0.395. So negative 0.395 equals 0.0907 alpha naught. So that gives us negative 4.36 about. Or we can just round that to negative 4.4. Yeah, let's do 4.36. So alpha naught is negative 4.36 degrees. So what that's saying is that our lift coefficient, CL, is equal to, if we put it in point slope form, it would be that minus 0, which doesn't do anything, equals the slope 0.0907 times the angle of attack alpha minus 4.36 degrees. Or sorry, that would be plus because this shifts it up. Yeah. All right. Because in the general form, it would be, so this is the equation that can tell us the lift coefficient at any angle of attack for our airfoil at 40 degrees, at least as long as we're in that linear region. Or sorry, not 40 degrees, 40 miles per hour. We just plug in the angle of attack, and that gives us the lift coefficient, as long as we're on that linear region. All right, now, this right here, in general terms, we would say CL is equal to this term we call CL alpha times alpha minus alpha naught. So this is the lift coefficient. This right here is the wing lift slope. So it's the lift coefficient per degree. So that's the wing lift slope in order to have units of 1 over degrees. That's the angle of attack measured in degrees. And that's the zero lift angle of attack. So now here's the thing though. The problem is our wind tunnel model is not exactly like the full-size aircraft. They're the same general shape, but our wind tunnel model was much stubbier. Our full-size aircraft that we simulated, the full-size wing, has an aspect ratio of 5.3 repeating, but the wind tunnel model had an aspect ratio of only 2.39. So much different. It's about or less than half the aspect ratio. And that changes how efficient it is, the amount of drag it makes, and also how much lift it makes. If we look back at our lift equation, imagine you had, so remember how wings make vortexes at the ends? And those vortices result, the induced drag, result in a loss of lift. So a finite wing, you're actually going to lose some lift. But the larger the aspect ratio, the closer the wing is to being infinite. Imagine you had an infinitely large wing, or it stretched, its wingspan stretched for infinity in all directions. Remember, our aspect ratio is the chord C, or the wingspan B, divided by the chord C. So AR is equal to B over C. If you had an infinitely long wingspan, you'd have an infinite amount of lift, but you'd also have an infinite area. And those two infinities cancel out to a finite number. An infinite wing would actually have a different lift coefficient than a finite wing. If we look back at our lift coefficient versus angle of attack graph, here's our real graph based on our finite wing. The infinite wing would actually have a steeper slope. It could create more lift at the same angle of attack because it doesn't have that induced drag problem. So the slope of this graph is CL alpha. The lift slope of an infinite wing, or just a pure airfoil, two-dimensional, where we don't have to worry about those wingtip vortices because the wing goes on forever. That's called C little l alpha. And we can account for this. There's an approximation made based on experimental results that the finite, so this CL alpha, that's the airfoil lift slope. All right, so there's an approximation that we can use. CL alpha, the wing lift slope, is equal to the airfoil lift slope, C little l alpha, times the aspect ratio divided by the aspect ratio plus 2. So we can use this. We had a finite wing in our airfoil. We can figure out its theoretical airfoil lift slope and then plug with the aspect ratio from our test. And then hold on to this for future reference. You'll need it. Just like you'll need this and this. So we can plug in the aspect ratio, which was what? 2.391 to solve for the airfoil lift slope. What the slope of this line would be if our wing were infinitely long. So our lift slope before was 0.0907 would equal C times little l alpha times our aspect ratio of our test section was 2.391 divided by 2.391 plus 2. So with a little bit of algebra, 0.0907 times 4.391 divided by 2.391 gives us 0.167 per degree. So that's the theoretical lift slope of this airfoil. Fun fact, if your units for angle are radians instead of degrees, a thin wing would have an airfoil lift slope of exactly 2 pi. All right, so now, this is CL alpha. We'll need this. I'm going to start. Let's find CL alpha for the real wing, or find the real wing's lift slope. That would equal the lift slope for our airfoil. So 0.167 per degree times the aspect ratio for the real wing, which if we go back to the simulations was 5.3 repeating. Over 5.3 repeating plus 2. So times 5.33 divided by 7.333. All right. So that's 0.121 per degree. So yeah, the real wing would be more efficient than what our wind tunnel test actually produced. Fun fact, if you want, you could also go ahead and make using your analysis over here, you could see if the slope of this linear region on your simulation matches that slope right there. And it should come out pretty close. I tested this last year. But anyway, so what this is saying now is for the real wing, the equation governing it is that its lift coefficient would equal 0.121 times the angle of attack alpha minus the zero lift angle of attack, which is negative 4.36. So minus a minus gives us plus 4.36 degrees. So, and we know to take off, we need a lift coefficient of 1.47. So let's see what angle of attack is required for takeoff. So 1.47 is equal to 0.121 times alpha plus 4.36 degrees. So that gives us 12.13 degrees equals alpha plus 4.36 degrees. So that means to take off, we need an angle of attack of about 7.8 degrees. All right. So we need an angle of attack of 7.8 degrees for takeoff. And let's look at this. According to this, our wing won't stall until around 20 degrees, according to our testing. That's when the lift starts to decrease. And in our simulation, it won't stall until around something like 12 or 13 degrees. So either of those is well under. So we have plenty of margin to take off safely. Hey, interesting fact that this makes 1,000 pounds of lift. So yeah, it's a little bit different from simulation to real life. There's a different zero lift angle of attack based on the model versus the simulation. So that's not quite exactly the same, but the slopes tend to work out. But anyway, so we know this plane can take off safely. In the next video, we're going to be looking at the cruise conditions and seeing whether or not it can cruise efficiently. That'll be our next test.